The Dead Sea is unique in many, many aspects. Its chemistry, its evolution, its composition.
Almost 1,400 feet below sea level, there's a lake so salty it can blind you if a single drop lands in your eyes. It's so dense that a human body can barely sink into it on purpose. For most of the last 3,000 years, that was reason enough to leave it alone. Nobody swam down. Nobody looked underneath. Then, in 2010, a small team of scientists decided that wasn't good enough anymore. They put on gear that had never been tested against a liquid this hostile, and they went down anyway. Before we uncover the mystery beneath the Dead Sea, hit like and subscribe, because the evidence changes everything. What they found at the bottom didn't just surprise them. It forced researchers to rewrite what they thought they knew about one of the most studied bodies of water on Earth. Towering mineral structures, dense colonies of life in a lake famous for having none, and a discovery trail that, strangely enough, leads all the way to a Nobel Prize in Stockholm. To understand any of that, you first have to understand something else. Why, for thousands of years, almost nobody dared to look. The lake that wasn't supposed to change for roughly 300 years. The Dead Sea sat in one of the most stable configurations found in any lake on the planet. It had 2 layers, and they never touched. On top sat a lighter layer of water, topped up every year by the Jordan River. Underneath sat something completely different, an ancient, heavier layer of brine that hadn't touched open air, hadn't mixed, hadn't changed in centuries. Scientists have a name for this kind of permanent split-layer system: meromixis. It shows up in a handful of lakes around the world, usually deep sheltered ones where nothing ever disturbs the balance long enough to break it. The Dead Sea was one of the most extreme examples anyone had documented. Here's the strange part. Even back in the 1930s, researchers at Hebrew University noticed something that didn't fit the lake's reputation. They found small numbers of microorganisms living in water that was supposedly incapable of supporting life. The name Dead Sea wasn't quite accurate, even then. But the observation didn't go anywhere. The lake's layered structure looked permanent. Funding follows urgency, and nothing about a stable, 400-year-old brine system screamed urgent. So the finding sat in a journal somewhere, mostly forgotten for decades. Keep that in the back of your mind. It matters a lot more later in this video than it seems right now. The permanence broke in the winter of 1978. For decades before that, water had been quietly pulled out of the Jordan River to irrigate farmland and supply growing cities upstream. Every year, a little less fresh water reached the lake, and every year, the top layer got a little saltier, a little heavier, inching closer to the density of the ancient layer sitting beneath it. It's easy to describe that as a gradual process, but think about what was actually happening physically. 2 layers of water, chemically distinct, one of them essentially untouched since before written history began, were slowly being pushed toward a tipping point nobody could see from the surface. There was no dramatic warning sign, no visible change, just years of quiet salt accumulation closing the gap between 2 worlds that hadn't mixed in longer than the United States has existed as a country. Then, in February of 1979, they matched. The entire lake turned over in one continuous motion. Top and bottom mixed for the first time in roughly 3 centuries, and the ancient bottom layer, the one with its own distinct chemistry, built up slowly since before recorded history, was simply gone. Researchers who had spent years carefully measuring that deep, untouched brine watched their subject disappear into the rest of the lake within a matter of weeks. it never fully went back to the way it was. The lake has flipped between stable and mixed states several times since 1979, but never for anywhere near as long as it held steady before. That single turnover is the moment the Dead Sea stopped behaving like the lake generations of scientists had studied and started becoming something else entirely, something still actively changing today. And as it turns out, that internal transformation was only the first of the lake's problems. A lake splitting in two, losing its ancient bottom layer, was just the beginning. Through the 1970s and 80s, the Jordan River kept losing water, not to one country, but to three, all drawing from the same limited source to keep farms irrigated and cities supplied. What used to flow into the Dead Sea at close to 2 billion cubic meters a year dropped to a tiny fraction of that. Some estimates put the current flow at around just 1% of its historical volume. Think about that gap for a second. Not a modest decline. A collapse to roughly 1/100th of what the lake used to receive every year, while the desert sun kept evaporating water off the surface at the same relentless pace it always had. Water going out, almost nothing coming in. The math only ends one way. The lake began shrinking by close to a meter of depth every single year. That trend has held for decades, and in recent years it's occasionally pushed past a full meter annually. Today, the surface sits at roughly 440 meters below sea level. Back in 1930, it was around 390 meters. That's a drop of close to 50 meters in under a century, and most of that loss happened in just the last several decades, meaning the rate of decline has been accelerating, not slowing down. The shallow southern section of the lake couldn't survive that kind of change. Historically, it rarely exceeded about 6 meters in depth, which meant it depended entirely on staying physically connected to the deep northern basin just to exist as part of the same body of water. By the 1980s, that connection broke. The southern end separated completely and dried into what is now essentially an industrial site, a network of man-made evaporation ponds. Here's where the story gets a little uncomfortable for anyone who's been to the Dead Sea on vacation. Companies in Israel and Jordan now deliberately pump lake water into those ponds and let it evaporate on purpose, so they can harvest potash, magnesium chloride, and other minerals used in fertilizer, cosmetics, and de-icing products. It's a real, profitable industry, but it means most tourists floating near the popular southern resorts today aren't floating in the ancient natural lake their grandparents might have visited. They're floating in an artificial industrial pond that covers tens of square miles. So by the late 20th century, the Dead Sea had become a strange hybrid, part shrinking natural wonder, part active industrial operation, with the two barely resembling each other anymore. Studying it stopped being simple. It became expensive. It became politically complicated, split across international borders and competing water rights. And none of that, not the shrinking, not the industry, not the international water disputes, was even the biggest reason nobody explored what was happening underwater. The real reason was much more direct. It could hurt you the moment you got in. Why no one dared dive. The Dead Sea is famous for one very specific, almost playful image: people lying back, reading a newspaper, floating without even trying. The water is nearly a quarter denser than ordinary seawater, dense enough that a human body barely sinks at all. But that exact same density that makes floating effortless makes deliberate underwater diving brutally difficult. A diver has to physically fight the water's natural push back toward the surface with every single stroke, using far more effort than an equivalent dive anywhere else on Earth would require. Floating is easy. Going down is a fight against the water itself. And that's the mild problem. The real danger is what the water does. If it touches you somewhere, it shouldn't. Getting even a small splash of Dead Sea water in your eyes causes intense burning and can seriously damage your vision. Swallowing a mouthful is worse. The extreme salt concentration can make your throat swell almost immediately, which can lead to choking within moments. This isn't a lake where you shrug off getting a little water up your nose. It's a lake where that mistake can become a medical emergency in seconds. For decades, that alone was enough to keep divers and researchers away. Ordinary diving equipment simply wasn't designed for a liquid capable of injuring someone this quickly, and there was no standard training program anywhere in the world that prepared a diver for it. You couldn't just take an experienced ocean diver and send them down here. The entire risk profile was different. That changed in 2010, when a team from Ben Gurion University in Israel partnered with the Max Planck Institute for Marine Microbiology in Germany to run the first serious scientific diving expedition into the lake. This wasn't a casual dive. The team wore full-face masks that completely sealed off their eyes and mouths, because even brief skin contact with the water was considered too risky to leave any part of the face exposed. Every single piece of equipment had to be tested against one question. Could it survive prolonged exposure to a liquid this corrosive without failing mid-dive? What they were actually looking for was almost quaint compared to the scale of what they'd end up finding. For years, people near the shore had noticed strange, rippled patterns on the surface of the water. Patterns that suggested something was pushing up from underneath. Nobody had ever confirmed what caused them, because nobody had been willing or able to go down and look. It had become one of those small, local mysteries that everybody had heard about and nobody had solved, filed away for decades simply because nobody had the means or the nerve to check. The divers found their answer almost immediately, and it turned out to be far bigger and far stranger than a few ripples on the surface. The craters and the impossible life. Beneath those surface ripples, the 2010 team found dozens of massive craters carved directly into the lake floor. Some measured more than 45 feet across and 60 feet deep, with steep walls layered almost like rings in a tree trunk, a visible record, built up over time, of exactly how each crater had formed. Fresh water was pouring up out of these craters from underground aquifers, jetting into the salty lake above, almost like an upside-down waterfall, at depths reaching around 100 feet below the surface. Picture that for a second. Cold, fresh groundwater erupting upward through solid, salt-saturated brine in total darkness, 100 feet down, in a lake most people assumed was just a flat, empty basin of dense water. That discovery alone would have justified the entire expedition. But what actually made headlines was what the divers found clinging to the edges of those craters. Thick mats of bacteria covered the rocks in multiple spots, a level of biological richness nobody expected to find in a lake famous by name for having no life in it whatsoever. And the contrast mattered here. The open water of the Dead Sea really is close to sterile. It holds only a few thousand microscopic organisms per milliliter, almost all of them a hardy, salt-loving type of microbe called archaea, built specifically to survive extreme salinity and basically nothing else. But right at the boundary, where the incoming fresh water met the surrounding salt water, right at the edge of these craters, researchers found communities that were denser and far more varied than anything ever measured elsewhere in the lake. Some of the rocks were covered in green biofilms, organisms using both sunlight and natural sulfur compounds from the springs to survive. And what really caught researchers' attention was how these microbes were pulling it off at all. Salt-loving organisms and freshwater organisms don't usually coexist, let alone thrive side by side. A salt-adapted microbe typically dies the moment it touches fresh water, and vice versa. But here, in a zone where fresh water and hypersaline brine were constantly colliding and mixing, something was tolerating both. Researchers openly admitted this kind of tolerance for sudden, repeated swings between two extreme conditions is something almost no other known organism can handle. This wasn't the first hint that the Dead Sea occasionally supported more life than its reputation suggested. Scientists had recorded exactly 2 visible algae blooms in decades of observation, one in 1980, another in 1992. Both brief, both treated at the time as strange, isolated anomalies. Nobody had connected them to anything. The crater communities suggested something very different. Not a rare accident, but a permanent, thriving ecosystem that had been quietly operating at the edges of underwater springs the entire time, completely unmapped, simply because nobody had gone looking. The 2010 dive was only the beginning. A second expedition followed in 2011 to study the springs in more depth, and the results were published in a peer-reviewed journal the following year, in 2012. That publication confirmed, formally and scientifically, what the name Dead Sea had been quietly wrong about for millennia. But even this wasn't the strangest thing researchers would eventually pull out of that lake floor. The chimneys nobody had seen before. More than a decade after those craters were first mapped, scientists were still sending divers back down. Not chasing a mystery this time, but trying to understand how the shrinking lake was continuing to reshape its own floor. In 2024, a team led by hydrogeologist Christian Siebert at Germany's Helmholtz Center for Environmental Research found something that had never been documented anywhere in the Dead Sea before. Towering mineral chimneys, some over 20 feet tall, up to 3 feet wide, standing upright on the lake bed, quietly releasing a shimmering fluid into the surrounding water. If you've ever seen footage of deep ocean hydrothermal vents, the volcanic chimney structures found on the sea floor, spewing superheated mineral-rich water, that's almost exactly what these looked like. Same general shape, same eerie shimmer, where fluid meets the surrounding water. But here's the twist. These Dead Sea chimneys have absolutely nothing to do with heat and nothing to do with volcanic activity. They're forming through a completely different process. Groundwater from the surrounding desert seeps down into old, thick layers of buried salt beneath the lake bed, dissolving them into an extremely concentrated brine. That brine then rises up through the lake floor, and the instant it makes contact with the Dead Sea's own water, the dissolved minerals crystallize on the spot, building solid chimney walls that in some cases can grow several centimeters taller in a single day. No magma, no heat source at all. Just chemistry, concentration gradients, and time. To prove where the material was actually coming from, researchers used a rare radioactive isotope, one that only forms when cosmic rays strike the atmosphere, alongside genetic traces of freshwater microbes carried down from the same aquifers that fed the 2010 craters. Both lines of evidence pointed to the identical conclusion. The salt fueling these chimneys was arriving from deep underground, not simply dissolving out of the lake itself. Confirming that took real detective work. 10 different research institutions, spanning fields from mineralogy to microbiology, collaborated just to nail down exactly how these structures were forming. And this is where the discovery stopped being just a strange curiosity and became genuinely useful. Because it turns out, the exact underground process building these chimneys is the same process responsible for one of the lake's most dangerous and least predictable ongoing hazards. The sinkholes. Nobody can fully predict. As the Dead Sea has continued shrinking, it's left behind something the tourism industry never wanted: thousands of sinkholes scarring the shoreline, most of them concentrated along the western coast. More than 6,000 have been documented since the 1980s, and new ones are still forming every year. Some researchers who track the numbers closely now put the current total well above 7,000. The cause traces directly back to the same underground salt layers behind those mineral chimneys. As the lake retreats, fresh groundwater from the surrounding hills flows into salt deposits that used to sit safely submerged underwater. That fresh water dissolves the salt from below, quietly hollowing out cavities beneath the surface. Cavities nobody can see from ground level, because the surface above them can look completely solid right up until the moment it isn't. Eventually, the ground can no longer support its own weight, and it collapses without warning, sometimes opening holes tens of meters wide and easily deep enough to swallow a building. Researchers studying the affected shoreline have calculated an average subsidence rate of close to 0.5 meter per year across the highest risk areas. This isn't an abstract hazard. It's had real, visible consequences. These collapses forced the closure of Ein Gedi, once one of the most popular resort areas on the Israeli side of the lake, back in 2016. Roads have been abandoned outright. Farmland has been destroyed. Entire stretches of shoreline are now fenced off simply because nobody can guarantee the ground underneath is stable. The very first documented sinkhole incident on record dates back to January of 1998, when an 8-meter deep hole suddenly opened up at a lakeside campsite, with no warning, no visible cracking beforehand, nothing that would have told anyone standing there that the ground was about to give way. And that unpredictability hasn't really improved since. Researchers studying the problem have been candid about the fact that predicting exactly where the next sinkhole will open remains extremely difficult. But the underwater chimney discovery gave scientists something they'd never had before: a genuine early warning tool. Because chimneys tend to form in the same underground channels that later go on to produce sinkholes on land, that connection between the two, one visible underwater, one dangerous on shore, is still actively being studied, with researchers from all 10 of those collaborating institutions continuing to dig into exactly how strong the link really is. A lake that once seemed too dead to matter has quietly become one of the more actively studied hazard zones in the entire region. And strangely enough, the single biggest scientific contribution the Dead Sea has made to the world had nothing to do with sinkholes or springs or chimneys at all. It came from something far smaller, and its story reaches all the way to Stockholm. The microbe that won a Nobel Prize. Remember that detail from the very beginning of this video. The 1930s Hebrew University researchers who quietly noted that the Dead Sea wasn't quite as dead as its name implied. That thread doesn't end there. It leads somewhere much bigger. In the late 1960s, researchers formally isolated a salt-loving microbe from the lake and gave it a name built from the Latin phrase for Dead Sea, Haloarcula marismortui. For a long time, it stayed exactly what it sounds like, a minor scientific curiosity, interesting mainly to a small group of specialists who studied organisms capable of surviving extreme salt concentrations. Nobody outside that narrow field had much reason to pay attention. That changed when structural biologist Ada Yonath went looking for an organism whose internal machinery was tough enough to survive being crystallized for detailed study under an X-ray beam. This matters more than it might sound like. Growing usable crystals from biological material is an inherently harsh process, harsh enough that it destroys the delicate internal structures of most organisms before they're ever useful for study. But this particular Dead Sea microbe had spent its entire evolutionary history surviving one of the harshest chemical environments on the planet. It held together far better than anything else researchers had tried, producing crystals that steadily improved in quality across more than a decade of careful refinement. That discovery kicked off a genuine research race, with multiple laboratories around the world racing to use these crystals for one of structural biology's biggest open problems. In 1998, researcher Thomas Steitz at Yale used crystals grown from that same Dead Sea organism to solve the structure of the ribosome's large subunit, the cellular machine responsible for building every single protein inside a living cell. By the year 2000, his lab and others had mapped that structure down to the level of individual atoms. In 2009, Steitz, Yonath, and a third researcher, Venkatraman Ramakrishnan, shared the Nobel Prize in Chemistry for that work. And this wasn't just an academic milestone. That ribosome research has since gone on to directly guide the design of newer antibiotics, drugs engineered to specifically target the ribosome of harmful bacteria, built on structural knowledge that traces back, in part, to a microbe pulled out of a lake most people assumed held no life at all. It's one of the more overlooked facts about a body of water most people only know from vacation photos and floating selfies. Put the whole picture together, and a clear chain of cause and effect shows up. A slow, decades-long loss of river water broke a chemical balance that had held steady for roughly 3 centuries. The shrinking that followed split the lake in two, turning half of it into an industrial evaporation site. That same shrinking process filled the shoreline with thousands of unpredictable sinkholes, while underwater, the lake's extreme chemistry kept nearly every explorer away, right up until a small team of specialized divers finally risked it in 2010 and found freshwater craters, dense pockets of unexpected life, and, in 2024, mineral chimneys that had never been documented before, anywhere. None of it is guesswork. The spring research was published in a peer-reviewed journal in 2012. The chimney findings appeared in Science of the Total Environment in 2024, and the Nobel Prize tied to this lake's own microbe is a matter of public record, sitting in Stockholm's archives right next to every other prize in the sciences. The Dead Sea got its name because nothing visible seemed to live in it. What people overlooked for centuries was everything happening beneath that still, salty surface. If this video gave you something, consider subscribing. It takes 3 seconds, and it genuinely helps us keep making content like this.